Hello everyone. Today we're going to talk about matrix calculus, and this is a brief recap in our optimization course. We'll focus today on two main things. First is calculating gradients of a function. It can be a vector function or a matrix function. And the second is calculating Hessians, which will be denoted as this, and probably this if you want. We'll start with some basic recap of some important matrix and vector operations. For example, if we'll consider matrix multiplication, we have two matrices A and B of shape m times n and n times p. The result of this operation is a matrix of shape m times p, and the naive multiplication will take O from n cube operations, but you can do less if you'll apply some fancy fast matrix multiplication algorithms like Strassen one, and also you have a physical limit. You cannot do it less than O from n squared, because that's the number of iterations of operations you need just to read all the unique information from the input arguments, right? What is interested here is the specific view of ij element of resulting matrix, Cij. That's the sum of the following way, which is presented here. What about matrix to vector multiplication or matvec operation? It's called matvec. The naive multiplication will give you O from n squared operations, which is better than matrix to matrix multiplication. And the ith element of these operations could be represented as follows. And some basic reminders, which are probably well known for most of you, is are presented here. For example, the matrix multiplication is not commutative, which means that you cannot just switch the order of operations. The result will not stay the same. When you transpose matrix multiplication, you have to transpose not only arguments, but you have also to inverse the order of multiplications, as presented here. For example, again, n times n, n times p, m times p, right? The result should be p times m, and again n times m and p times n here. Okay, that's correct. What is more interesting in context of our today's lecture is this property, which are quite important here for our practical tasks. And actually, that's a property of scalar product of two vectors, where you can take the matrix from one argument and place it to another with transposition. And you can also do it in the following setting. For example, if we have, let's say, some Z transpose, and here you have, I don't know, P transpose and matrix B, and here we have this scalar product, right? You can also take your matrix B and place it here on the right with transposition, which is also important. And the difference between those two cases is here you have matrix A on the left And here you have matrix B on the right, I mean on the left of the vector y, and here the transposed matrix A is still on the left of the matrix of the vector x. But here again matrix B on the right, and here matrix B transposed is also on the right of the vector z. So you can like change the position of this matrix. It is very useful in our context. Next we'll go to the idea of gradient, and the gradient concept is actually one of the cornerstone idea of optimization, machine learning. Suppose you have a function of n variables or a vector function which returns a scalar. The simplest example of this function is just a linear function. For example, here is C transpose X, where C is some constant vector and X is our vector variable. And the gradient vector is actually nothing else but the vector of all partial derivatives here, which is also in n-dimensional Euclidean space. So it's just the analog of simple derivative when your function takes a vector as an input. What about the second derivative? And here we have Hessian or Hesse matrix. And sometimes people call Hessian as a derivative, as a determinant of this matrix, but that's a question of the notation, so it doesn't matter for us. And that's just the matrix of all possible second order derivatives of the function, right? So it's squared matrix of size n, of shape n times n. But if your matrix if your function takes not a scalar or not a vector as an input, but a matrix, the gradient concept will slightly change. Like, for example, suppose we have a function which takes X matrix as an input and returns a scalar, for example, determinant, or trace, which is just a sum of all diagonal elements of a matrix. The derivative, the first order derivative of this function, will have a shape the same as an input, and let me write it here. The derivative of such function with respect to a matrix X is nothing else but the matrix of all possible derivatives by all entries, input entries, right? So E for all, let's write this, for all I and J. So it could be a matrix if your input is a matrix. Like in a similar way, if your input is a tensor, your first order derivative will be a tensor. Okay, next we'll go to the Jacobian, which arises in a case when your function returns a vector as an output. That's a typical case for machine learning. We typically have some transformation which takes a vector and returns a vector as well. And in this case, each output of your function, like first output, second output, and nth output of your function, forms the same like vector of derivative as gradient, as it was in gradient case. And now they form a matrix which is called Jacobian or Jacobi matrix. This table summarizes all the ideas which were presented above, and actually this table is about first order derivative, which means that, for example, suppose your function maps from x space to y space, and here is this x space and y space. And suppose x is Euclidean space of dimension 1, which means that your input is, so that's the input, that's the output. Your input is scalar. Here your input is vector, vector, and matrix. And again, scalar, scalar, vector, scalar. Here is the gradient shape, right? Gradient shape. In case your input and your output are scalars, you have the simple derivative, right? That's it. That's the derivative, and the shape of the gradient is also a scalar. Important case when your input is a vector and your output is a scalar is a gradient vector. Again, when both your input and your output are scalars, sorry, are vectors, then you have this Jacobian matrix as a thing that reflects first order derivative information. And in case you have a matrix as an input and a scalar output, again determinant, trace, you have this df divided by dx yj. That's the matrix. Matrix of all possible first order derivatives with respect to all input entries. And now we'll go to general concept of taking these derivatives, and we'll go to ideas of derivatives and the way to compute them. But firstly, we'll briefly say that actually the gradient vector is not just the vector of derivatives. It's also a very important thing because it reflects it is the direction of steepest ascent of your function. Steepest ascent, which means that this vector, which means the gradient vector. At the same time, minus gradient vector, or which is called anti-gradient vector, reflects the direction of steepest descent, which is interesting in optimization, because we're typically doing minimization of a function, right? Let's go to general concept of taking these derivatives and calculating these gradients. We'll start with the gradient, and the core concept here is concept of taking differential of a function. And typically, we'll start with some point x in Euclidean space, and a little difference, small difference here, dx. When we say little in terms of a scalar, we can say that dx tends to 0. But when dx is also a vector, we say that the norm of dx tends to 0, right? For example, Euclidean norm, second norm. And now we'll consider a difference between function values in these points, in point x plus dx minus f from x. And when we tend dx to 0, this difference is also tends to 0, right? Because like in the limit case, when dx is 0, then the df should be equal to 0. But the limit of the ratio, right, of this ratio, like remember in the scalar case you have this limit in the scalar case df divided by dx, and that's actually the derivative at this point. Geometrically, what does it mean? Geometrically, it means that if you have some like function. It could be a vector valued function, a function that takes a vector as an input, right? But returns a scalar. Now we're talking only about this function which returns a scalar, but still this approach will be still valid for a function that returns a vector and a function that takes a matrix as an input. It's very, very interesting here. And you consider some point x and consider small neighborhood of this point, and actually you just building this best local linear approximation of a function, and you know this angle actually reflects this ratio which we are considering here. But in a vector case, they are connected like this. Let's consider a simple example here of calculating a differential. By definition, let's consider example of a linear function f from x is equal to c transpose x. Then df is c transpose multiplied by x plus dx minus c transpose x. For sure, that's actually c transpose dx or scalar product between those vectors c and dx. And we can conclude here that this vector reflects the linear connection between small difference in a function value and small difference in a vector space, dx, which means that actually the gradient vector here is just c, vector c. And the whole idea will be the following. We'll calculate the differential of a given function and bring it to the view like something multiplied by a small difference dx. Calculating of a differential will require using some simple properties. Most of them are actually quite reasonable and pretty obvious, but some of them require derivation, and let's consider some of them which we will use in our examples. Suppose matrix A and B are constant matrices, as well as matrices X and Y will be a variable matrices or like input matrices. And that's pretty obvious though that dA should be equal to 0, right? Because the difference of a constant matrix is 0. As well as pretty obvious that we can easily take constant scalar alpha outside the differential sign here. So differential of a constant multiplied by a matrix is equal to constant multiplied by a differential, right? And here actually you can think of X and Y sometimes here, not only matrices but vectors as well, because vector is a specific case of matrix. You can take constant matrices, constant inputs outside the differential sign. Differential of a sum is equal to sum of differentials. Differential of transposition is a transposition of a differential. It's quite reasonable. And these two formulas are pretty important to us. For example, about differential of a scalar product. That's just the sum of two things: differential of a first argument multiplied by a second argument, and first argument multiplied by differential of a second argument. Here, for example, is differential of a ratio of a fraction, and when we're talking about a fraction, we cannot just place matrix y at the denominator here, because we cannot divide by a matrix, right? That's why phi here is a function, some function which can take matrix or vector as an input and return a scalar. Here, this derivative is not actually obvious, and we'll derive it. We'll derive it by hand, like manually. Later, at the end of the video. And here is one more important point that is needed to be discussed. And that's the scalar product between matrices. What? We only talk about scalar product between vectors. But there are multiple ways to define scalar product between matrices. And I'll write like one of the most obvious way and one of the most which is like assumed when nothing else is specified. That's the trace of the product A transpose B. Note that matrices A and B are of the same shape. For example, M times N and M times N. You can take a scalar product between the objects of a similar nature, right? And here we have N times M, M times N. So great, you have this trace of a squared matrix. Note that scalar product does not depend on the order of the multiplication. And immediately we have the following property, that we can just switch the matrices and the result will stay the same. Interesting here is that this way of defining, this definition of scalar product on the matrices is consistent with the Frobenius norm. And Frobenius norm is actually nothing else but a square root of a sum of all squared elements of a matrix. Okay, let's go through the examples, and we'll firstly focus on calculating gradients. That's the typical task here. And then we'll go to the Hessians. Again, gradients and Hessians. Consider this simple example of a quadratic function. And our way, like what we're gonna do is first we calculate the differential of a function. Differential is equal to la 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 la. And then we'll have to bring it to this form. Differential is equal to scalar product between la 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 and this small difference dx. And actually, what we got here is exactly a gradient here. Okay, let's do it. First point is, let us slightly rewrite the notation of a given function. And we can say, without any loss of generality here, that f is equal to 1 divided by 2 multiplied by a scalar product between vector x and vector ax plus scalar product of vector b and vector x plus c. Now, that was the first point. The second point. Now we'll calculate the differential of f using the properties above, which we presented here. Okay, let's do it. Firstly, I'll just rewrite what was there instead of f. Okay. And now I have the differential of a sum, right? That's the sum of differentials. d 1 divided by 2 x ax plus d of bx plus dc. Most obvious part here is the differential of a constant. It should be equal to 0, right? But what about these differentials? Firstly, I can easily bring this half outside the differential, right? Since it's constant. I write it here. Differential of a scalar product, x ax plus, and let us here calculate the differential of a scalar product. And let's take a look. How should we do it? Here we have the answer. Differential of a scalar product is the sum of two scalar products, right? But we can see that one of the inputs of this scalar product is a constant b, which means that I can just write directly that this differential should be equal to scalar product of b and dx. You'll receive the same answer if you write it explicitly using the formula of differential of a scalar product, since db is equal to 0. Okay, let's go further. Here we have to use this formula. Differential of a first argument multiplied by a second argument plus first argument multiplied by a differential of a second argument. Scalar product plus b dx. I'll switch sides in the first scalar product because the scalar product does not depend on the order of multiplication, which means that I can write here ax multiplied by dx. Next, interesting quest here is taking the differential of a vector valued function, right? Because ax is a vector, but still you can, since a is a constant here, not a variable, not an argument, you can bring it outside a differential sign, right? So it will be x multiplied by a dx. I'm doing this very in step-by-step manner, right? A lot of things could be done here in mind or much faster, but I will write it explicitly. And next thing, half multiplied by ax dx, and take a look at this scalar product. Remember that we need to receive in the end something multiplied by dx, but here we have a dx. And what are we gonna do here? We have to remove this a somehow, and we can easily do it just by transposition, right? I mean that I can just take this a here and bring it here, plus a transpose, don't forget to transpose here, dx plus b dx. And now, using the linearity property of, using the linear property of a scalar product, we can conclude that the result will be the following. Sorry. If you'll take a closer look at what is here, you have dx, dx, dx. And you can just take all other things outside the bracket, right? And now we can conclude that this exact expression is a gradient. Very simple. Now we'll go to the second example, and we're going to calculate the differential of the following negative exponential function, right? And again, first step is to write it as follows: minus exponential to the power of minus x times x. That's true. And now we're gonna calculate the differential of this function. D from minus exponential to the power of scalar product. We can easily take minus outside the differential sign, here minus differential of exponent. Now we have to remember all these formulas for standard calculus, for standard derivatives. Differential of exponential is just exponential multiplied by differential of an argument, which means following: minus exponential to the power of product multiplied by a differential of an argument, minus x times x. Actually, for simplicity, we can use this notation as this minus exponential to the power of tralala is equal to f minus, again, could be taken outside the differential sign, and let's go further. We have here actually dx multiplied by x plus x multiplied by dx, which are the same things. And actually minus f multiplied by 2x dx, right? We just calculated this sum because this is equal to x dx as well. And again, we have something multiplied to a dx, to this small difference. For example, here we have minus f multiplied, minus 2fx multiplied by dx, and this is actually a gradient, which means that the gradient is equal to 2 exponential to the power of minus x transpose x multiplied by x. Let's verify that our answer has a correct shape, right? That's a scalar. This exponent is also a scalar. This is an n-dimensional vector, right? 1 times 1, 1 times 1, n times 1. And the result is a vector, as it should be. Let's consider third example of calculating a gradient of a matrix function. And here we have this scalar product of two matrices, and we know what it is. So we just calculate the differential of this function. So differential of scalar product of s and x minus logarithm of determinant of x. I'm writing ln here, assuming that the logarithm is by the basement of e, right? So ln means directly logarithm of e, of exponent. Next, we have the differential of a difference. Super easy. Now we have differential of this scalar product minus differential of a logarithm of a determinant. Let's go. First we have a scalar product here and differential of scalar product, and that's pretty easy because you know the answer already. That will be scalar product of constant matrix S. S is a constant matrix here because x is a variable, and dx. Next, we have to calculate the differential of a logarithm, and we know the answer. I'll write it here, that differential of a logarithm of some function phi is actually d phi divided by the argument of a logarithm. So we have d, which means differential, of a determinant of x divided by an argument, which is a determinant here. Here we have to use the formula of differential of a determinant, and we'll use it as it is here, determinant of x multiplied by a scalar product. Let's verify it. Yes. And here minus t means inverse transposed matrix, which is just inverse of transposed matrix or transposition of an inverse matrix. The order doesn't matter here. Without any doubts, we divide the fraction by determinant of x, assuming that this determinant should not be equal to 0, because we have a logarithm of a determinant here. That's why it couldn't be 0, right? Because we couldn't calculate the logarithm of a 0 argument. Moreover, what is more, we should have determinant greater than 0 in order to take the logarithm here. Okay. Next, we have this very simple, sorry, minus here, notation. And voila, we have the answer that the gradient of this function is actually s minus x inverse transposed. Yeah. It is easy to verify that the answer is a matrix, as it should be. And you can easily see that in terms of taking the gradient of a matrix function, which means with respect to a matrix, is slightly harder, or actually doesn't at all, because it uses the same procedure as in the vector case. Okay, let's go here and take a gradient of this function as our last example here. Sorry. I'll write it on the next page. A logarithm of scalar product ax and x. A logarithm of a scalar product ax and x. And we know that A is symmetric, positive, definite matrix. Okay. What is df here? Is d from a logarithm from this ax and x, which means actually d from a scalar product divided by a scalar product itself. And this scalar product could be easily computed. I mean, the differential of this scalar product could be easily computed, which is just a dx multiplied by x plus ax dx. Here is just axx. Next, we have the same idea as it was before. We have here a transpose x dx plus ax dx. Taking into the account that A is a symmetric positive definite matrix, we can conclude that A is equal to A transpose. Here we just derive it by this. And we have 2ax divided by ax multiplied by x. And this is all scalar product with difference dx, which means that the gradient of the function is 2ax divided by axx. That's it. That's the vector as it should be. Now we'll go to the calculating of Hessians. The procedure of calculating the Hessian of a function is almost the same. You have to take differential one more time, with one small exception. You treat the old difference dx as a constant now, and we'll refer to it as dx1, which means first order difference here. And then just calculate differential of a differential. And after you'll do it, you'll have this, and you have to bring it to the one more form, which is explanatory here. This is the form of scalar product between something multiplied by our first difference dx and this dx, which is actually our next variable dx here, dx2. Let's take a look on the examples. We'll start with our first example of a quadratic function. I'll go to the next page, but we'll work on this example. So suppose we have this differential here as scalar product between 1/2 a plus a transpose multiplied by x plus b dx. Now you treat this dx as a constant, so we'll explicitly write here dx1, and after it you just calculate differential of a differential, so d by f, or just d from df. Let's take a closer look here. D of this df go to here. Okay, we have inner product or scalar product x plus b times some constant dx1. Okay, that's just the differential of a scalar product, which is well known for us. That's actually, like, note that dx1 is a constant here. That's why we can just leave it here and take a differential of a first argument. So 1 divided by 2, differential of a plus a transpose x plus b, square bracket means nothing here, just brackets, dx1. That's it. We'll go further. That differential is very easy to expand, right? It's just a plus a transpose dx, because differential of b is equal to 0, times dx1. And here we can explicitly write that this new difference dx will be noted as dx2. And our goal is bring it to this form. Some matrix multiplied by a dx1, which is overall multiplied in a scalar way to the dx2. So we have to leave only dx2 as an argument of a scalar product, which means that we have again to bring our matrix here, right? That's not a problem for us. So what we are doing here, okay, let me write it step by step. dx2, and here we have half of this sum dx1. Now I'll switch the arguments of a scalar product, and we'll have 1 divided by 2 half of a plus a transpose dx1 multiplied by dx2. And I'll take a look at the formula that I have here. Here I have Let's do it straighter. Yes. Something multiplied by dx1, which is multiplied in a scalar way to dx2. Let's take a look. That's it. I have it. This matrix multiplied by dx1 and multiplied in a scalar way by dx2. That's why I have an answer here. The Hessian is actually half of this sum. And that's a squared matrix, as it should be. Let's take a closer look to our second example, which was written here. Let's take this second derivative. For this purpose, I'll probably add one more page here. Yes. And I'll write explicitly here this is differential. Okay. What do I need? I need a differential from the first step. Firstly, I need to calculate a gradient here. And from the first step, what I have here, that df is equal to minus f multiplied by 2x dx. And now I'll explicitly write here 1, which means dx1, and I'll calculate the second differential, or differential of a differential, or differential of minus f multiplied by 2x dx1. And note that I'm treating dx1 as a constant here, but x is a variable. Okay, firstly I can bring the minus outside the differential, but then I have a differential of multiplication. Okay? Minus differential of f multiplied by scalar product 2x dx first. And then I have this idea, minus df multiplied by scalar product 2x times dx1 minus f multiplied by a differential of this scalar product. Okay, that's it. Now I need this, and actually I know this. I know what is df. I've already calculated it. Let's write it down. I have this minus, and then I have one more minus. Let's write in this way. Or actually I can just write a plus, right? Let me write a plus here, because one minus is here and the other minus is here. Plus f multiplied by 2x multiplied by dx. And note that here I do not write this dx as dx1, because this difference was like, we met this difference at the second step. That's why we have to place it as a differential, as a difference here, as a dx, not a constant dx1. The constant was only at the beginning here. Now all the differences which we are calculating here are like valid differences, valid differentials. Okay. That was the df. And this should be multiplied to scalar product 2x dx1. Okay, minus f multiplied by this 2 dx dx1. First thing here is that I can take f outside the brackets here. F outside the brackets, and here I have the following multiplication. 4 then x transpose dx multiplied by x transpose dx1, which are just a scalar products here, minus 2 dx transposed multiplied by dx. We can write scalar product in any way we want, both A transpose B and figure brackets A and B. And also I can do this, right? I can take 2 outside the brackets also. Now we have to bring it according to the form which is compliant with our formula. Our formula was following: scalar product of Hessian multiplied by dx1 times dx2. That was our formula. Okay. Which means that we almost already have this formula in our second summand here, but we do not have this formula here. That's why we'll go step by step here, slowly write it in the following form. Here is, oh, sorry, I forgot 1 here, right? Yeah, he should be 1. Here we have dx1 transpose multiplied by dx, and this dx is actually this dx2. And here we have to do something with all these like manipulations. And first thing that I would like to write here is just to switch these scalar products between each other, which means that I'll write just x transpose dx1 multiplied by x transpose dx. Okay, that's closer. What do I mean here? I mean here is that just 2f multiplied by a scalar product of 2 x transpose dx. Okay, let me write it in like separately. What do I have here? This is actually equals to a scalar product of dx, which is a dx2 actually, and the rest, but this rest should be transposed, right? Because AB equals to A transposed B. That's why I have to write it down in the following way: x transpose dx1 multiplied by x transpose, and this whole thing is transposed. Okay. But that's actually pretty okay for us, because we'll write it down. We know that x transpose dx1 is a scalar, and transpose scalar is just a scalar. But here we have to transpose transposed vector. It's just a vector itself. which means here we have x transpose dx1 multiplied by x minus dx1. Here we have dx. I've just used a linearity property here. For example, here is a scalar product between dx1 and dx in the same manner. Okay. Next, what is left here is bringing this dx1 outside the brackets. Let us do it. And this is actually pretty simple. We know that x transpose dx1 is a scalar, and the scalar could be placed both on the left and on the right from the vector, which means that I can just easily write here x multiplied by x transpose dx1, right? Here I have this, which is a scalar, and here I have this, minus dx1 dx. I'm almost done here. Now I have to take a dx1 outside the bracket here. What do I have here? I have here 2x transpose minus something multiplied by dx1. And here is dx. But what should be left here? Is it just 1? That will be not correct, because x transpose is actually a matrix of size n times n. And here should be also a matrix which is identity matrix, because this identity matrix multiplied by dx1 is just dx1. So we just take it outside our brackets here. Okay. And actually, what do we have here? We have here that this second differential is equal to this 2f multiplied by 2x transpose minus identity matrix dx1 multiplied by dx, and here we can place 2. And that's the Hessian, actually. That's why the Hessian matrix is this 2f multiplied by 2x transpose minus identity matrix. That's the answer here. That's it. That were examples about calculating a Hessian matrix here, which is slightly harder than calculating a Hessian, but not like insanely harder or extremely harder. At the end, let us consider the formula that was promised. So our next goal is to calculate a derivative of a determinant of matrix. We'll consider a simple case, relatively simple, with an assumption that determinant x is not equal to 0, which means that the matrix is invertible and non-degenerate. And moreover, we suppose that matrix has eigendecomposition. But still, the overall answer will be valid even without these assumptions. Note that differential is this difference of a function value with difference in argument tending to 0 and the relation between differential and a gradient is the following. Okay, let's consider, like by definition, what is differential of this function. That's the difference between determinant of x plus dx minus determinant of x. The first thing could be rewritten in this way. I can take x outside the brackets. Here I'll have identity matrix left and inverse matrix here. Because if you open the bracket here, you'll receive the previous result. That's correct. Minus determinant of x. Next, I have to use the property of like the determinant of the product of matrices equals to the product of determinants, which means that I can write here determinant of x and determinant of I plus x inverse dx minus determinant of x. I can again take determinant of x outside the brackets, and I'll have here the only determinant which is left of I minus 1. And again, I matrix is just a matrix of all ones on the main diagonal and all the zeros except this. Now I have to pause it, and I will use the property that the determinant actually is a product of all its eigenvalues of a matrix. Product of all n eigenvalues. Lambda I from I plus x inverse dx. Next, I'll also use a property that the eigenvalue of a matrix of such form is equal to 1 plus eigenvalue of another matrix. Let me write it. This 1 plus eigenvalue of matrix x inverse dx. That's it. And now I'll open this product. Like I multiply all entries to each other, and the first thing which I'll have here is just 1. If I'll take only ones everywhere from all brackets, from all things. Next is when I take 1, all ones except one bracket, where I take lambda I, and next I'll have this sum from 1 to n of all lambdas, x inverse dx here. And later I have a lot more summands here, a lot more, and all of them are inherit one important property, is that they all have the degree of dx entry greater than 1. But since dx is a small difference, is a small matrix, we can just skip them all and write them in the following way. All from dx norm. Because, you know, when norm of dx is small, tends to 0, all other entries, all other summands in this sum have dx in a degree greater than 1, which means they are very, very, very small. That's what it means. which means that we can approximately skip all these entries, skip all the summands, and have only this 1 plus sum of all lambdas x minus 1 dx. And note that sum of all eigenvalues is just a trace of a matrix, which means that this thing is a trace of matrix X inverse dx. Okay, let me return to the previous writings. What do I have here? I have this determinant of X multiplied by 1 plus trace of X inverse dx minus 1. That's it. And I'll have only determinant of X multiplied by a trace of X minus 1 dx. And note that my goal, however, at the moment we've proved the formula, but we can also calculate a gradient here. We note and we remember then x minus transpose and dx scalar product is nothing else but trace of this matrix, right? Because it should be transposition of a transposition. Double transposition means nothing here. That's why we can continue and write the following thing at the end. Scalar product of determinant of x multiplied by x inverse transpose and dx, which means a gradient here. And the gradient is a matrix, which is cool. That's it. That was the proof for some specific case, but the formula is valid for any matrix X, for any square matrix X. But the proof should be a little bit more accurate, but we'll skip it for today. That's it. That was the material about matrix calculus. I hope that now you'll know how to calculate gradients and Hessians of a given matrix or vector function. Thank you.